All right, now where were we? So in part one, we derived a way of representing a particular dictionary. So if you hand me a basis and you hand me this equational form, we found a way of representing a particular dictionary using only linear algebraic notation. In other words, if you give me that basis, I can reconstruct the whole thing, the whole dictionary from scratch using only the basic inputs to the LP, such as the vectors C and B, and I guess X, and the matrix A. What we need to do now, though, is find some way of turning that insight into an actual algorithm. So the simplex algorithm is a lot more than just looking at one dictionary. In fact, arguably, the important part of the simplex algorithm is how we move between dictionaries. So if we go back in time and take a look at what we ended up with at the end of part one, we ended up with this. So if you hand me a basis, and I assume, given whatever basis you hand me, I can construct the restriction of my vector C and the columns of my matrix A to the basic variables and to the non-basic variables, then our dictionary looks like this. So we were, for example, able to determine that the values of each basic variable in that dictionary can be determined by this equation, because we know that, obviously, the non-basic variables equal 0. Additionally, if I'm looking at a dictionary and I want to know the objective value, I can determine it with this. The issue is, okay, so we have this dictionary, but how do we run the simplex method? How do we decide whether we're looking at an optimal dictionary? And if we aren't, how do we choose an entering variable and a leaving variable? And how do we perform a pivot? So that's the point of part two. And then part three is going to tie up some loose ends, including a very big loose end, which is when are certain matrices invertible. I know you've all been sitting on the edge of your seat waiting for that, as well as to talk about some implications on things like the dual simplex method. In the meantime, we're going to struggle. I think the biggest struggle in part two is going to be dealing with, as usual, sort of our ongoing war against notation. And so we'll start by talking about what the basis should be. So we saw in part one that if you give me a basis and I have some way of computing, for example, the coefficients of the basic variables in the objective function, the values of each basic variable, we'll call that xb, and the columns of my constraint matrix A for the basic variables, and similarly the columns for the constraint matrix A for the non-basic variables, the coefficients of the original objective vector for the non-basic variables, and this, although we usually expect x sub n to equal 0 because non-basic variables always equal 0. If you gave me a choice of basis, then I would be able to derive that sort of pseudo-dictionary, that linear algebraic representation of a dictionary. What we're going to do in this part is assume that our basis itself, the way we actually store the basis, is just as a set of indices. So if my basis happens to be x1, x4, and x5, it's reasonable that because all of my variables are numbered as x's, that I could just represent that as a collection. Let's see if I can draw curly brackets correctly. That's about as good as I'm going to do today. A collection of just the indices of the variables that are in the basis. And I guess it might be relevant in some cases to also know the indices of non-basic variables, but as long as I know how many variables I have, if I have one of these two sets, I could always construct the other one because it's, in a sense, the complement of the basic variables will be the non-basic variables. So if you hand me a feasible basis, so you give me this LP in equational form, and you hand me some feasible basis where the size of the basis is what we expect, so we use our usual convention that M represents the number of constraints, and we know that if our constraint matrix A has, if it has m rows, then we expect there to be m slack variables in a dictionary form, and I guess congruently we expect that there will be m things in the basis at any given step. So if you provide me that constraint matrix, I know in advance how big the basis is going to be. So if you provide me that, we now can write out the simplex algorithm in strictly linear algebraic terms. And we're going to try and do that in a manner that uses linear algebraic notation as much as possible. We would rather not have to, for example, iterate over a vector and look at each element in a sort of algorithmic sense. I'd rather define the whole thing in terms of basic fundamental linear algebra operations like matrix multiplication or computing an inverse or solving a system of equations. Although there will be a couple of places where we do have to define some more ad hoc operations, for example, choosing leaving variables, as we'll see. So in this part, we'll talk about these sets B and N to be sets of variable indices. And then I want to expand a little bit about what this paragraph is saying. So we saw in part one, I'll make myself a new slide. We saw in part one that our typical, we might have some objective vector, let's see, 0, 5, 6, 0, 0, 4, 7. here's our objective vector, and we know that, of course, the indices of my objective vector correspond directly to each individual optimization variable, or each individual variable. We know that in this case, some of these could be slack variables. We don't care. Every variable is a variable. We also know that if you provide me with a particular choice of basis, let's say in this case my basis is would be x2, x3, x6, and x7. Then we can construct this vector xb, which would correspond to the values only of the basic variables. Now, the issue here is that I want to make it clear that in the interpretation that I am going to use, so xb here would be the values 5, 6, 4, 7. In the interpretation that I'm going to use, I'm going to treat xb like it's a vector. But the key thing is I am not going to treat it like it is a separate entity from x. In other words, when I talk about x sub b, certainly that does refer to these 4 elements, but it doesn't refer to its own distinct vector. It just refers to what we would call normally a view on the vector x. And I think this is congruent if many of you have probably used Python with NumPy or you've used MATLAB. There is functionality in array programming languages to do this, where you have an index set and you index some vector or array by this index set, and it gives you back the values corresponding to those indices. But when you modify it using that notation, you are modifying the original. So if I were to write something, we'll just ignore this for a minute. If I were to write something in my pseudocode that looks sort of like this, if I say assign to xb the values, 1, 2, 3, 4. If I write this, which is an assignment statement, what I am saying is modify the vector x. So x sub b is not a separate entity from x. X sub b is just a way of interpreting x where I only see certain indices. So if I wrote this assignment statement, I wouldn't be modifying some extra vector xb. I would be saying, please modify the original vector x at the indices referred to by my set b. And we'll have to be a little bit, I'm not going to actually write this exact statement for a couple of different reasons, one of which is this is a set, which means it has no order. But one key thing I need you to keep in mind as we go forward is that when I talk about vectors xb or cb or ab or an, I am using this assumption that what I'm really doing is just pulling out specific elements of this big vector x. I'm not constructing some secondary vector, except, I guess, as a transient intermediate result. That means if I attempt to modify xb, I am modifying elements of the original vector x. That's a key thing to observe. And you might be wondering, okay, why would I bother with this long disclaimer instead of just doing the modification directly into x? And the reason is because depending on how you implement it, how you store the set b, how you store the vector x, exactly how you do that mapping is sort of your business if you choose to implement this version of the algorithm. And I want to keep the discussion that I'm going to have sort of implementation agnostic. And I feel like this is a way, despite the long disclaimer, this is sort of a way to do that. The other thing we have to keep in mind is that there is a notational shift between this and the book. And I think unlike a couple of the other notational shifts I've had to do, this is one that you'll probably agree I had no choice for. So the Vanderbeek book also refers to our basis as a collection of indices. However, for some reason, Vanderbeek uses these symbols to refer to our index sets. And then, to refer to what we're going to call A, B, and AN, in other words, the columns of my constraint matrix for basic variables, the columns for non-basic variables, the Vanderbeek book just uses B and N. Maybe you can see there's a bit of a problem there if I'm going to be talking about this. Reading it is one thing, but talking about it is another. What do I call this? Cursive B? MathCal B? And what do I call this? How do I differentiate these? That's going to be a huge mess. So I'm going to adopt a stripped-down approach, where instead, when I use uppercase B, I am referring to, for example, an index set. That will be the set of indices of my basic variables. If I want to talk about a restriction of my constraint matrix, I will use the notation A sub B. The reason I like that is that I think that's more consistent than Vanderbeek's version, because Vanderbeek does use XB and CB, and I think that because XB and CB conceptually are sort of the same thing as AB, they are the restriction of parts of my LP to the basic variables, it makes sense to name the restriction of the constraint matrix consistently. So I've got AB, CB, XB, AN, CN, and XN. And that means if I use the names B and N, I'm referring only to index sets. So if you take a look at the derivation in the book, it's a good derivation. It's pretty much the same as what we have here. I've made a few simplifications to notation later on as well, but it's deriving the same algorithm, but beware that they are using different notation for a couple of things, in particular for this. Okay, so what do we have to do? I'm going to put this remark aside for now and just go over in a broad sense what we need before we have the simplex algorithm in linear algebraic terms. So what do we do in the dictionary-based simplex algorithm? Well, the first step of any iteration is to decide whether we're done. It's to examine the objective row and then decide, based on the objective row, are we already looking at an optimal dictionary? And I mentioned this in part 1, but there is a sign flip. We're going to see there are a few sign flips in this linear algebraic derivation. There's a sign flip that we have to be conscious of. So I'm just going to scroll back and we'll take a look at this pseudo dictionary from part 1. Notice that in the objective row of this derivation, we've got, there's our objective value. Okay, that isn't, that's weird looking, but it's not that controversial. But notice that this thing, Zn xn, is subtracted off. The whole thing is subtracted off. And that means that when we go looking for objective coefficients, the sign that we're looking for will end up being the opposite of what we're used to. Normally, to find an entering variable in a dictionary, we look for something whose objective coefficient is positive. But that means in this representation, we're going to be looking for a non-basic variable whose coefficient in Zn is negative because we have this sign flip here. So just be aware of that. And I'll talk more about that in a minute, so the slides will also come back to that. So at the first step of our linear algebraic simplex method, we want to examine the objective row. Now, we don't actually really have to compute this unless we need it. And you might remember, we don't really need the objective value except if we're done, except we actually have an optimal dictionary. But we would compute it somewhere around step 1. So we compute this objective coefficient vector, and actually I should be careful. This is sort of inaccurate. It's not really a coefficient vector directly. It is the values of my basic dual variables. But obviously they correspond to objective coefficients if we consider that sign flip. So I compute the vector Zn using the same derivation that I had in part 1. And then I ask, is the dictionary optimal? And remember that elements of Zn that are negative correspond to variables that have a positive objective coefficient. So if no variable has a negative coefficient in Zn, that means I'm staring at an optimal dictionary. And if that happens, I'm done. The algorithm's over. If not, then I want to choose an entering variable, subject to whatever pivot rule I'm using. I want to choose a leaving variable, again with ties resolved by my pivot rule, and then I want to perform a pivot. One interesting thing we'll notice is that although this is the same algorithm that we've been using on dictionaries, just written out in different terms, we are able to put the work in a different place. We'll notice later on that the actual pivot step could be implemented with nothing but maybe 2 set modifications, so swapping some indices around. Whereas, of course, in the dictionary notation, the pivot step is very complicated. It requires a huge amount of work. What's happening in the linear algebraic version is a lot of that work is being offloaded, for example, up here, where we know in the beginning of the dictionary-based method, we don't have to do any work to examine the objective coefficients at the beginning of an iteration because they're just sitting right there in the dictionary. So we'll notice that by writing things out linear algebraically, we can move some of the operations between parts of the algorithm. Now, all of this is going to be a moot point unless we start our iteration with our pseudo dictionary, with our basis feasible. We know that the simplex method can't do anything unless we're staring at a feasible dictionary. So one thing we have to assume is that, as usual, the values of our basic variables are non-negative. So that's certainly a mandatory assumption if we're going to try and rewrite the simplex method as we know it in linear algebraic terms. This statement that all of my variables, my basic variables are non-negative, we know that in a dictionary terms, this is essentially saying that the basis is feasible. That's it. In this case, for the linear algebraic method, we have given this formula, this provocative formula to compute the values of my basic variables that requires the computation of a matrix inverse. So not only do we have to make the reasonable assumption to state the invariant that at the beginning of each iteration the basis is feasible, that the values of each non-basic variable are negative, that itself is uncontroversial. That's a requirement of the algorithm. But in order to move forward, because of the way we phrase this time, we also have to move forward assuming that this matrix A sub B is invertible. And, obviously, there's that word again. I swear we're going to talk about that. So the beginning of part 3 will put that to rest. I know we've been stringing along on this idea that we can keep assuming that that matrix is invertible. It is. In all of the cases where the dictionary-based method would work, that matrix will be invertible. There are cases where it might not be invertible, but those correspond to choices of basis that wouldn't work in the dictionary-based method either. We'll come back to that in part 3. So if we keep assuming that matrix is going to be invertible, how do we run the simplex method? So step one, we've got to look at the objective row. And as the slide is pointing out, so this is the expansion in sort of our pseudo dictionary of the objective row. It'll be this constant minus this dot product here. So our a linear combination of our non-basic variables. Now, because of the minus sign, what we usually expect, that is looking for our entering variable as one with a positive coefficient, it means it's going to have a negative element entry in Zn. So if we discover that every element of Zn is greater than or equal to 0, then there is no potential entering variable. And that means we're staring at an optimal dictionary. And so the slides are now saying what I just said. Now, if we find that that's the case, so if I discover that I'm staring at an optimal solution, so every element of Zn is non-negative, well, then I have an optimal dictionary, and I suppose then I need this. If I want to end the algorithm and return the optimal objective value, obviously I need the optimal objective value. I think it turns out you don't actually need to compute it until you get to that point. So I think only then will we bother to actually compute this product, because it seems like this might be a bit labor intensive. So we don't need it for every iteration, just for iterations where we've discovered that the dictionary is optimal. On the other hand, suppose that the dictionary isn't optimal. Well, then we have to perform another iteration. We have to perform a pivot, which means we have to choose an entering variable. Okay, so we know that we can't fully specify this because our choice of pivot rule has an impact on our choice of entering variable, but we can talk about how we would find candidates for entering variables. So we know that this vector Zn contains, I guess I shouldn't have put it this way. Zn contains the negation of each objective coefficient. It corresponds to objective coefficients, but the vector Zn has been designed so that it's congruent with the values of the basic dual variables. And so it has that sign flip built into it. But the vector Zn is where we would go to look to decide what could be our entering variable. And so how we actually choose that entering variable can differ depending on the rule. But remember that a variable is a candidate to be entering if in the dictionary form it has a positive objective coefficient, and due to the sign flip here, that means it'll have a negative entry in Zn. So suppose I were to use the largest coefficient rule. Well, in that case, I would choose my entering variable xj, I would choose the index j, to be whatever index of z. Notice that I'm using the big vector z, not zn. And the reason I'm doing that is because if I care about the index of the variable that I'm choosing, so xj, it's really easy to go from the big vector z to an index. So if this is my big vector z here, so I don't know, 0, -1, 2, -1, 4, then I know that so this is x1, this is x2, this is x3, this is x4. Maybe we should have more zeros in there to correspond to the basic variables. I know that if this is my vector z, the coefficients that match up with each element will just match the indices that I'm sitting on in the vector. So if I end up at index 2 of my vector, then I'm looking at the coefficient that would go with x2. Whereas if I talk about zn, well, I think zn would actually just be these middle 3 here, then it might take more work to go backwards and figure out the index. Now, implementation-wise, it's up to you how you do that. I like using the big vector because of that obvious correspondence between the index of each element and the index of the corresponding variable. So if I chose my entering variable by the largest coefficient rule, I would want to choose the smallest negative value in z, because that would correspond to the largest coefficient once I flip the sign, and then that would become my entering variable. If I were to use Bland's rule, then of course I would just choose the first index in z, because that would be the lowest numbered thing, by the obvious correspondence of indices. So I have a quick example here. So if my basis is x1 and x4, and my non-basic variables are x2, 3, and 5, and Zn equals this thing, so Zn, of course, has size 3 because there are 3 non-basic variables. The big vector z, well, the big vector z, I mean, I just plug in those values from Zn in the corresponding locations. And I also can observe that this is the index for x1, there's x2, there's x3, there's x4, and there's x5. So the largest coefficient rule would choose the smallest negative value, that's -4, which is in the column corresponding to x5. So x5 would be the entering variable. Bland's rule would choose x3 because it's the lowest numbered thing. So if I just go from left to right through z, then I will hit x3 as the first candidate to be the entering variable, the first thing whose entry is negative, and that would become my entering variable. Now, as far as choosing the leaving variable goes, we don't have as easy a path. And the reason is because we need more information, and the information doesn't really fall right out of the linear algebraic derivation that we've done. So we need, as you may recall from dictionary form, we need to look at a particular column of our dictionary when we're computing the choice of leaving variable, and the column we care about is, well, I guess we also care about the constant column, but we mostly care about this column corresponding to the entering variable. And that's all well and good. The issue is that in our linear algebraic derivation, we treat the entire constraint part of the dictionary as one big matrix and vector product. And so it's a little bit harder to see how we're going to look at those elements. And so we do sort of have to take apart our notation a bit. So one thing we know is that the values at the beginning of each iteration, the value of every non-basic variable, every basic variable is equal to this product here. We figured that out, take my word for it, apparently on slide 34. That was about 1 million years ago in slide terms, but also I'll admit it was 3 days ago that I recorded part 1, but I'll trust myself and assume that slide 34 did indeed give a derivation, so scroll back to that if you want the derivation again. So the question is, at the beginning of our iteration, this gave the value of every basic variable. We know, I guess intuitively, what we need to do to compute which variable will be the leaving one, which is I've chosen an entering variable, xj, to enter the basis and therefore to take on, ideally, a non-zero positive value. The question is, how much can I increase xj such that all the constraints are met? And we know from the dictionary form that what that question really translates to is, how much can I increase xj before one of my current basic variables goes negative? So we don't want to increase it too much or else something will go negative and that's not allowed. We will, however, increase it as much as possible, and that will result in one, maybe more than one, but certainly one basic variable going to 0. And that'll, of course, be our leaving variable. It will leave the basis and xj will take its place. The issue is we need a little bit more information than we can get out of formulas like this. So if we look at this in dictionary form, here's an example of a dictionary. Suppose that I've chosen x2 to be my entering variable. Well, to decide what's going to be my leaving variable, what I would normally do is I would walk down the column for x2, and I'd use the constant column as well, and the two of them together would be used to compute bounds on my entering variable. So for example, this would give the bound x2 is less than or equal to 8 over 4, which is, I'll just simplify that, 2. If x2 is ever bigger than 2, x4 is going to go negative. That's not allowed. And then this would say that x2 is less than or equal to 4 over 3. All right, and so I can do, and then this just has no effect whatsoever, and this also has no effect, because we know that no matter how much I increase x2, there's no way x7 is going to go negative. And so we know that both the coefficients themselves and the sign of the coefficients plays into what my candidates for leaving variable are, and then ultimately what the choice of leaving variable is. Anything without a negative sign is ignored. And then from among the remainder, we want to choose whichever has the smallest bound. I think that would be this one. So x5 would become my leaving variable. The question is, what do we do in linear algebraic terms? We might already recognize that this column here, so 8, 4, 1, 2, this is our vector xb, the values of our basic variables. And we also might recognize that, I'm going to clear this, we also might recognize that none of this stuff is relevant. The only variable we're modifying is x2, the entering variable. Everything else in the dictionary is staying put. So all of the other non-basic variables are staying 0. I don't need to consider every single coefficient, only the ones corresponding to this column and this column here. So I'm going to choose to write that out this way. For now, I'm just showing off the ultimate structure I'm going to use. I'm going to go through a full derivation of this in a minute. So what I'll do is I'll simplify down what I need. I've got xb that contains the current value of each basic variable. And then, as we did back when we initially derived the simplex method, we're going to view what we're doing here when we compute the leaving variable through the lens that my goal is to increase the value of x2. Because doing so is going to increase the objective value. I'm increasing the value of x2. Let's suppose that I increase x2 to equal some number t. And ideally, it says a potentially non-zero value. Ideally, we want to increase x2 to a positive number, to increase the objective value. We know by now that that's not guaranteed. There are cases where x2 has to equal 0. We get a degenerate pivot. But we want to increase x2 to some value t that is ideally non-zero, but certainly is never negative. If we do that, the question is, what effect will that have, if I set x2 to be t, what effect will that have on the values of my basic variables? And we can compute that really, well, the current value of each basic variable is this. If I increase x2 to have some value t, I can write out the new value of each basic variable using this equation. Notice the negative sign. And that seems a bit counterproductive. If I'm increasing x2, why have I decided to phrase this in terms of negative numbers? Hopefully you notice that this is, if I look at these two columns, this relationship does map on exactly. It's just that I've done a sign flip. I've gone from saying -4 to -4, and -3 to -3, and then +1 to -1. And I know you might look at that and say, it just seems like we're flipping signs for no reason here, Bill. What's the point? Doesn't this just make everything more complicated? So yes, frankly, it does. I see your point. That's actually why I added this slide. But the reason that the minus sign is in there is because in our linear algebraic derivation, when we derive the value of the basic variables in terms of everything, not just in terms of their this constant column, there was a negative sign in our derivation. So I've added the negative sign here to make it more obvious later when I talk about this where that negative sign is coming from. The reason why I wanted to show it off in this diagram is when we do it this way, if we define, I'm going to ultimately, if I set x2 to be t, the change in my basic variables will be the current value of each basic variable minus t times this vector here, which I'm going to call, I better make sure t isn't included in my little box. I'm going to call this vector delta xb. And the key thing to note is that if I go looking for a choice of leaving variable using the coefficients that are in delta xb, the only things that will be candidates are things whose value in delta xb is positive, because that would correspond to the cases where it's negative in my dictionary representation. So that means if it's 0 or if it's negative in delta xb, these are not candidates to be the leaving variable. So I'm going to derive this again from scratch. In my original intent, I added these slides at the very last minute, by which I mean between part 1 and part 2, I went and added these slides because I noticed how confusing this looks. I'm going to present a full derivation of where I get delta xb from, but I think this gives us some context to understand why I'm going to end up looking for positive numbers as opposed to negative ones like we're used to. So only those elements that are positive in delta xb correspond to candidates to become the leaving variable. Okay, so back on slide 34, in ancient history, we ended up with this formula. In our pseudo-dictionary, we were able to figure out that the basis rows are defined by this. And we know that most of the basis row in a dictionary, like if we go back to this dictionary here, most of the basis rows are useless to us if we just care about the values of the variables. If I ask you, what is the value of x5? Oh, it's 4. We're done. All of this is irrelevant. So wait, why is that all there? Well, these relationships are important because they help us with pivoting. We need to state them, even though we know that numerically they're always going to equal 0 because all of my non-basic variables equal 0. So I have this derivation of this entire tableau of not just this, but all of this stuff too, in terms of the values of my basic variables, and that's this. My basic variables, the basis of my dictionary is this thing, which is the value of the basic variables when all of my non-basic variables are 0, minus this whole thing. And this is the statement of this part of the dictionary. And we saw that in part 1. Normally, of course, if all of our non-basic variables are 0, then this vector is 0, which means that this product is the vector 0, which means that this product is the vector 0. And of course, that means this can be ignored. But the problem is, when we're talking about computing the leaving variable, we are talking about the case where we increase one non-basic variable, one element of xn, to be non-zero. And so suddenly, this product has a lot more significance. And what we have to do is try and find a way of turning this product, which refers to all non-basic variables together, we need to find a way of turning this product into something that we can work with, some way of just pulling out the coefficients for the non-basic variable that we're choosing to modify. Okay, so I want to increase one variable, and the problem is that linear algebraically, that taking this product apart is rather difficult. And unfortunately, the description I have to give is laden with a number of layers of indirection. And so, I don't know, put on your gumboots, let's wade into this notational swamp here. In the case where we only want to increase one variable, we know that only one element of xn will be non-zero. So this part maybe isn't controversial. At the beginning of my iteration, xn, well, all of my non-basic variables were 0. That I should expect. But then I chose an entering variable. So when I did that, suppose I chose x2 to be my entering variable. Well, then I want to see, if I give x2 a value t, some positive value, what happens to my basic variables? Notice that when I do that, there's only going to be ever one element of xn that's non-zero. Just one. That's going to be my entering variable. Okay, so that's what the first bit of this is saying. Now, unfortunately, we have to wade further into this paragraph, and I did write this paragraph, so I can be hard on myself if I want to. This is not my best prose. I would argue that it is mathematically valid, and there isn't really an easier way of writing it out in words, but it's ugly. So allow me to provide you a dramatic reading. So I know that only one element of xn will be non-zero, so the product an xn will evaluate to xj times the column of an corresponding to xj. Okay. By the definition of an, so what's an? An is a matrix whose columns are the columns of the big matrix A corresponding to our non-basic variables. Okay. By the definition of an, this will just be the jth column of the larger matrix A. It says it in such a nice, smooth way that you almost want to believe it. And so it gives you this. It says that this whole product, in the unique case where I'm only changing xj to be non-zero, so I give xj some value, this whole product evaluates to AB inverse multiplied by this thing. This is a single column of A, the big matrix A, so column A sub j, multiplied by the new value of xj. And I would pretty much forgive you for staring at this for a minute and then saying, so Bill, I see what you've done here is you've taken a bunch of letters and you've arranged them into rows and then separated some of them by spaces. And you've purported that what you've ended up with is something that's supposed to approximate language. Is it possible that the language you've used is understood by literally anybody on Earth? And I would argue that it's hard to say. So the question is, if we stare at this and we conclude that this does not look like any statement of anything approaching a fact or an opinion or anything that could be considered useful or knowledge or information, what are we supposed to do? I foresaw this, and so I have an example. So here's an example where I've got my non-basic variables are 3, 5, 8, 9, x3, x5, x8, x9. Okay, and here's my matrix an. So an is going to be the columns of my larger matrix A corresponding to x3, x5, x8, x9. And so I should expect, therefore, that this column goes with x3, this column goes with x5, this one goes with x8, and this one goes with x9. Now suppose that I have chosen x8 to be my entering variable. So x8 is a non-basic variable. Suppose I choose it to enter. If I do that, then I guess my goal is going to be to set x8 to some positive number t. And then I want to look at what is the product an xn going to look like. So this is the product an xn here. So I know that if I set only one non-basic variable to a value t, then every other non-basic variable is just going to equal 0. So the product an xn will be the matrix an multiplied by this vector where only one element is non-zero. And if you run through this matrix multiplication, you can verify that the result is just going to be, maybe I can show one more step. It'll be 3 times t, 7 times t, 11 times t. And I like to pull out the t there so it's more obvious that what I actually end up with is just the column of an that went with my non-basic variable. And we know that this column will be, it happens to be the third column of an, but in general it will always be, if my non-basic variable is x8, this will be the 8th column of the bigger matrix A. So we'll call this A sub 8, which will refer to column 8 of the big matrix A. We don't really know or care exactly what column it's going to be in an. That's sort of irrelevant, because we know that depending on what the other non-basic variables are, this could be anywhere inside of an. We know, though, that by consistency, because we know that the location of our non-basic variable in xn will match the location of that column in an, the thing we end up with will always be column 8 of the big matrix A. So this product ends up just equaling the new value of x8 multiplied by column 8 of my matrix A. So that's what's happening there. I know that this description does not help with that at all. I had to write it out a few times myself before I figured out how to phrase it, and then before I figured out what it actually meant. So if we use that information, let's define this vector delta xb to be this product. So remember that a few slides ago, the product that we were concerned about was this thing. So AB inverse AN XN. When we took apart this wording, we were able to figure out what this product equals. It's going to be A sub j times the new value of my entering variable. What I'm going to do now is I'm going to package together these two things, so this matrix and then this vector, and I'm going to call this delta xb. And it turns out that it is going to end up equaling that vector delta xb that I had in the previous example. And notice that, just like before, I want to keep the new value of my entering variable separate from that, because I don't know it yet. I have to compute it somehow. I just want xb to be that vector of these coefficients here. So I define delta xb to be that. Now, because of the notation that I've insisted on, where these restricted vectors, the n's and the b's, aren't real vectors, they're just views onto other big vectors, that means I have to define this vector delta x for every x variable. But because all I care about are basic variables, I'll just define the non-basic part of x to be 0, and then delta xb to be this product I just came up with. So if I set xj, some particular choice of xj, to a positive value t, then that, basically by these examples we just went through, and intuitively due to this thing we saw earlier, if I set xj to be some value t, the basic variables will go from having these values, which we computed at the beginning of the iteration, to this. This will be the new value of each basic variable. In other words, the current value minus the impact of modifying xj. And if we play around with this, if we factor it out, we end up with, if I set xj to equal t, we end up with t times delta xb. In other words, we get exactly this thing that we saw in that example earlier. So if I modify, in this case, x2 to a value to equal a value t, the basic variables are affected by this equation here. This is the new value of each basic variable. So that's how I got to that point. So what do I want? Like, what's the point of doing any of this? The point is to find a leaving variable. What I know is that under no circumstances can a basic variable go negative. And this is the value of my basic variable subject to a particular change in my entering variable, and I need to find a value t such that this is always obeyed. But on the other hand, I do want to make sure that I can make t as large as possible. In other words, what I sort of want to do is maximize t such that this equation remains greater than or equal to 0. And if I parse that in terms of trying to actually solve it for t, what I'm really doing is, just like in the dictionary-based method, I am looking at the lowest bound on my entering variable. So for example, my entering variable is xj, and I was able to compute the bounds. Xj is less than 2/3, xj is less than 7, xj is less than, I don't know, 6/5 or something, then what I would choose to be the value of my entering variable, the value t, would be the lowest such bound, the minimum across all of the bounds. Now, this min function obviously looks a bit more complicated than that, so let me unpack it a bit further. I'll do that a bit more on the next couple of slides as well. So the first thing is, I only care about looking at basic variables, obviously. Notice, though, that inside the min function, this ratio here is computed using the indices of actual x values. So if I look at a particular basic index, this value xi is just the value of the current value of the variable x sub I. I'm only looking at basic indices, but I am indexing the big vector x. I'm not looking at the vector xb or xn or anything. Same story for delta x. When I say delta xi, I'm saying look at the ith element of this big vector, which of course contains all of the basic variable values, or the coefficients, but I'm using indexing, absolute indexing, with the regular index of each optimization variable. This condition here, delta xi is greater than 0, is my way of saying I don't want to try and compute the ratio in cases where this particular basis row doesn't relate to the entering variable, or where it isn't bounding the entering variable. So if we look at our previous example, what I'm talking about are cases like this. So here, we notice that delta x is equal to 0, because x6 and x2, my entering variable, aren't related. So there's no point. There's no way x6 is going to impose a bound on x2. And also because if I tried to compute the ratio, I'd be dividing by 0. Similarly, this situation, where there is a relationship between x2 and x7, but it isn't going to put a bound on x2. I can increase x2 as much as I want, and it's not going to affect x7. Notice that that's negative in my derivation, in delta x. So I don't care about either of these two cases. And that's why in my min function, I am only considering cases where delta xi is greater than 0. So not just greater than or equal to, but greater than 0. This does raise a concern because we know that if I use a min function with restrictions, there is this concern that what happens if every single element of delta xi actually is less than or equal to 0? Well, then I'm taking the minimum of 0 things. That's a bit of a problem. We can't do that. What does the min function evaluate to if you give it no arguments? And so to avoid too much of a notational headache, I'm just going to handle that special case out of band. So if you were to implement this, the way you would handle that situation is if you ever end up with a delta x where every single element is negative or 0, don't even bother computing t. If when you're picking up the terms for these ratios, you notice that there are no qualifying elements of delta x, what that's actually saying is that the dictionary at this step is unbounded. Notice that if there isn't anything in delta x that puts a bound on my entering variable, I can increase my entering variable as much as I want. And in that case, we can make a few arguments to how to handle that. One of them is to interpret the value of t to be infinity, in which case, of course, the LP is unbounded. To be honest, from a practical standpoint, implementation-wise, if you notice that, just end the algorithm. Just return and say this LP is unbounded. But it is at this step, as in the dictionary-based method, it is at this step that you would detect unboundedness of the LP. Okay, so we've done that. We've computed the value t that the maximum value we can increase our leaving variable or entering variable to. Now we need to know what is the leaving variable. Well, the leaving variable will be some basic variable that actually achieves this ratio, that actually puts that bound on the entering variable. So first we compute the value of our entering variable, then we go back through and actually find a particular basic variable that satisfies that puts that bound on my entering variable. And I have to be a bit vague here because we know that more than one basic variable could be tied as a leaving variable candidate, and how to resolve the tie depends on the pivot selection rule. So if multiple variables happen to have this property, then the pivot selection rule determines which one to choose. Bland's rule, of course, would always choose the lowest numbered candidate. And it turns out if we think about what this is really saying, so I'm going to back up again and we'll look at our example further. So, not this example. There we go. So here I would go through and I would compute the usual ratios. So for my entering variable x2, I would say, well, this puts the bound that x2 is less than or equal to 8 over 4, which is 2. And this puts the bound x2 is less than or equal to 4 over 3, which is smaller than 2. And what you might notice, if you're used to this, I mean, we've done this all semester, is that, okay, yeah, these variables put these bounds on my entering variable, but once I've chosen a leaving variable, so I choose this as my leaving variable, it turns out that the value of x2, when I'm done the pivot, will be 4 over 3. And we've sort of relied on that a lot. And so that's true here too. If I compute this, in this case, I would say that means the value of t is 4 over 3. That's the largest number I can increase my entering variable to such that no basic variables go negative. That's fine, but it also happens that t will be the value of my entering variable once the pivot is complete. And that's what this slide that I got to was saying. So because of the way I chose t, assuming the LP wasn't unbounded, the value of xj when it enters the basis will be t. Additionally, if we actually, I didn't make one point I was supposed to make there. Additionally, notice that means that x5, the leaving variable in this case, will equal 0. I'm going to set x2 to a number such that this that 3 times x2 actually equals 4. And that means that x5 will equal 0 when I'm done, which also we expect. Because if x5 wasn't 0, how would we take it out of the basis? Okay, hopefully it's all the scrolling I have to do. Okay, so additionally, so what this is saying is my entering variable's actual value in the basis will be t. So I actually already know that. Additionally, my leaving variable, of course, has to be 0 because I'm forcing this variable to become non-basic. Another thing to observe is the value of t is guaranteed to be positive. And I can explain why that is. So when I went to compute t, I computed it to be the minimum of these ratios. And what do we know? Well, we know that the value of xi, so the value of any of our basic variables, has to be non-negative, or else the dictionary wasn't feasible to begin with. We also know that delta xi has to be positive because I said so. It's in the argument to the min function. It says that I only consider cases where delta xi is positive. That means that this ratio always has to be greater than or equal to 0. And that in turn means that t always has to be non-negative. And actually, yeah, I should be careful here. Technically speaking, this should be non-negative. So I'm framing this in terms of non-degenerate pivots, but in the event of a degenerate pivot, t would equal 0. In any case, t would never be negative. That means that xj, when it enters the basis, will have the value t, which will be feasible. xi will end up equaling 0, which again is still feasible. Xi is non-basic, so we expect that. This guarantees that, also assuming that t was chosen properly, that is, it's the minimum bound on the entering variable, this guarantees that the whole basis will be, the new basis I'm constructing will be feasible as long as the basis that I started with was feasible. And it's reasonable to assume that because that's an invariant we've been assuming all along, that we can't run the simplex method unless we have a feasible basis. So what's next? Well, we have our entering variable, we have our leaving variable, now we need to do the pivot. So what we noticed all along was when we needed to compute things like the values of basic variables or the objective coefficients, we went and did a bunch of math. And that means in a sense that every piece of information that we need is being recomputed during every iteration of the algorithm. So what do we really have to do to update our basis? And I would argue that, at least in the naive case, certainly if you want to update as little information as possible, you can write it so that all you actually have to do to perform a pivot is update the index sets. So I've decided that xj is entering the basis and xi is leaving. So I add, my new basis is the current basis plus xj with xi removed. And my non-basic variables, complementarily, I guess, I'm going to add I to my set of non-basic variables and remove j. And it turns out that that's it. Unless I happen to be storing information about x, z, and zeta, which I don't have to do because I can recompute them every time I need them, I don't have to do anything else at step 4. And of course, that's a contrast to the dictionary-based method where I do tons and tons of work at step 4 because I'm essentially rearranging the entire dictionary. But in exchange, whenever I need things like the objective coefficients, I just go grab them. So here, I recompute the objective coefficients up here, and in exchange, I do very little work down here. So this would be sort of a naive pivoting step. I update b and n, and then if I ever need these again, like at the next iteration, I just recompute them from scratch. There isn't, although this hopefully to you rings some alarm bells, it seems a bit wasteful, there is a certain numerical advantage to this, because notice that the basis and the non-basic variables, these sets b and n are stored as sets of integers, so they're not going to be subject to weird floating point stuff. And if I fully recompute all of this at every iteration, notice that what I'm using to recompute it are all fresh copies of the original data. So the matrix A, the vector B, the vector C, the vectors, different bits of the vector C. All of that stuff, I can compute CB for a particular basis by just filtering my original vector C. And nowhere in the algorithm do I actually modify A, B, or C. They are the original inputs. So if I do this, if I fully recompute, then at every single step, I am obviously doing some numerical stuff to get my values of x and z and zeta, but I'm not having numerical errors that pile up, because unlike the dictionary-based method, where the numbers you had at the beginning of iteration I are used directly as input to what you get for the beginning of iteration I plus 1, here I could compute fresh new values of each thing in each iteration that are unaffected by rounding errors or whatever that might pile up. On the other hand, this still is a little bit wasteful because there are some computations we can avoid. There are certain things that we already know. So one example would be, we actually know the new values of each basic variable already using information we've computed up in steps 2 and 3. So if we don't want to fully recompute everything, we can save a bit of work by reusing some computations we've already done. So this suggestion is supposed to happen before we update the sets of basic and non-basic variables. In other words, this modification applies to the old set of basic variables. So what do we know? We know that we chose a value t such that I can, I guess the largest such value t such that this, the new value of each basic variable, will always be non-negative. So I've chosen the value t. To update the values of each basic variable, I can just apply this relationship that I derived earlier. I just set the basic variables to equal their current value minus t times delta xb. We know because of the way we derived t that this guarantees this operation will always set xi to equal 0. So t was set to be the minimum bound on our entering variable xj, and we know from what we saw earlier that that will force one particular basic variable, maybe more than one, but at least one basic variable to go to 0. If we perform this modification, it will do that. Xi will end up equaling 0. Then we'll set xj to equal t, which we already saw is going to be its value in the new basis, and now we're all ready to take xi out of the basis. Its value will be 0. We can now put it as a non-basic variable. We can add xj as a basic variable. So we can recycle some calculations to avoid fully recomputing xb. And if we look at the full recomputation, to compute xb from scratch using my new basis, I need this matrix inverse multiplied by a vector. And although it's true that apparently I need the matrix inverse anyway, so I might have it lying around, the matrix and vector multiplication probably requires more work than just subtracting one vector from another, or subtracting a scalar multiple of one vector from another. So the next slide is going to show pseudocode for this linear algebraic simplex method. It is the same algorithm that is given in Vanderbee's book, but it is not the same pseudocode. It has been distilled a bit because Vanderbee has deliberately given pseudocode that's a bit more verbose to illustrate the impact of duality more clearly. So an example would be in figure 6.1, Vanderbee actually gives side-by-side pseudocode for the primal and dual simplex method. And he's written it in such a way that it's obvious where the primal and dual stuff is happening in both sides, on both versions of the algorithm. So an example would be, he actually computes a vector delta z as part of the process of recomputing z, even though in our derivation we don't need that. We can just compute z from scratch. The reason he does that is to make it more obvious that just like how we compute delta x as part of the computation for a leaving variable in the primal simplex method, we would compute delta z as part of the computation of the entering variable in the dual simplex method. So he actually explicitly does that even in the primal method to illustrate more clearly the connections made by duality. I'm not going to do that in my version because I think that version exists. You can go look at it. I want to show a version that is as compact as possible. So both the pseudocode on the following slide and Vanderbee's pseudocode are fundamentally the same algorithm, but they have a few notational differences. One other very odd difference is that Vanderbee computes these ratios, the ones for this, he computes them in reverse. So delta xi appears on top, which I'm not a fan of because it means we have a bigger problem with dividing by 0. But it is, if you needed a point of reference for pseudocode, both are fine. So here it is, our primal simplex method with linear algebra. So what do you pass in? If you're going to call this, you pass in the equational form a, b, and c. You also provide me a feasible basis. And I know it feels like that's not fair, but we know that just like in the dictionary-based method, you don't actually start running the simplex method until you have a feasible dictionary, a feasible basis. And finding a feasible basis can often be a thing. So we can solve an auxiliary problem, we can use some shenanigans involving the dual simplex method. I'll talk about those in part 3, but it is reasonable to assume that you cannot run the simplex method, the primal simplex method, until you have a feasible basis. So you pass in a feasible basis, and then, just like I mentioned a couple of slides ago, I am not going to fully recompute xb at each step. Instead, I'm going to update it based on what I previously had. The problem is, I need some initial value for xb. So what I'll do before I start iterating is I will fully compute xb and xn using the formula. And then if I notice that the values of my basic variables are not all non-negative, so in other words, if any element of xb is negative, then you lied to me, you handed me a basis and you told me it was feasible, but it wasn't, and so here's where I'll throw an exception or something. I mean, who cares how I handle this? This is an error, the algorithm is done if we get to this point. Otherwise, assuming the basis was indeed feasible, here is my iterative process. So first I compute my vector zn, or my vector z, which corresponds to objective coefficients. If I notice that z is non-negative, then what I really have, well, that means that fundamentally there is no nothing in the objective row has a positive coefficient. That's one way of interpreting it, but it's also worth noting, and one of the reasons I like using zn and allowing that sign flip is, what this is also saying is that we have a dual feasible dictionary. And if we have, because remember that the value of Zn are the actual values of each basic dual variable. So I've already done the negation that I would need to do that, in the negative transpose. That means that if Zn is greater than or equal to 0, my dictionary is dual feasible. And because I had this assumption that I have a feasible basis in my primal dictionary, I have a primal and dual feasible dictionary. That is the definition of optimality. So if I get to that point, I compute and return the objective value, and we're done. Otherwise, the dictionary is not optimal. It is not dual feasible specifically. So I choose an entering variable, and in this case, we can't be too specific because it depends on the pivot rule. I choose some index among my non-basic variables such that the z value for that index is less than 0. And then I choose my leaving variable, so I compute my vector delta x, and this is a little bit, I've condensed this step, but I compute these ratios, I compute the value t, but while I'm doing that, I have to check for unboundedness, because we know that if the min function ends up with no arguments, that's technically not allowed. So somewhere in this computation, you should check that there is at least one ratio that I'm allowed to compute, one value of delta x that's greater than 0. If not, the LP is unbounded, then you would return. So take a look at slide 66. We talked about that earlier. If the value t can be computed, so if the LP isn't unbounded, then choose the leaving variable among the candidates. If there are more than one candidate, we have to ask the pivot rule to help us out. So again, can't be too specific about that. When we're done, it's time to pivot. We'll update the values of our basic variables, and then we will adjust our basis. And that's the end of the iteration. And that is the primal simplex method via linear algebra. So we're not done the lecture because we have to talk about it, but we have to tie up some loose ends. In part 3, we have to talk about why it was reasonable all this time to assume this matrix was invertible. We also finally get to understand why we call this thing a basis. So at the very beginning, many of you heard the word basis in May or something and thought, well, that word has a meaning in linear algebra. Why are we using it here? And we'll talk about that in part 3 as well. And we'll also talk a bit about the dual simplex method with linear algebra. And then finally, we'll talk about things like two-phase methods. So how to find a feasible basis if the problem is initially infeasible.